If you live in the United States, there's a good chance you've driven across state lines without even thinking about it. Maybe you've crossed from California into Nevada in a few hours, or taken a road trip from Texas to Florida, watching the landscape slowly change outside your window. Distances feel conquerable here. 4 hours, 10 hours, even 3,000 miles coast to coast. It's long, but it's doable. You can measure it in tanks of gas, playlists, and rest stops. Now I want you to take that instinct, that deeply American confidence that any distance can be crossed with enough fuel and determination, and hold on to it for just a moment, because we're about to confront a distance that makes the entire width of the United States look smaller than a single step. Proxima Centauri, the nearest star beyond our sun, is 4.25 light-years away. That sounds almost friendly. 4.25. Not a million, not a billion, just 4.25. But that number hides a truth so extreme that it breaks intuition. A light-year is not a measure of time, it's a measure of distance. The distance light travels in 1 year, moving at 186,282 miles per second. In 1 second, light could circle the Earth 7.5 times. In 1 year, it travels nearly 6 trillion miles. Multiply that by 425. That is the gap between us and our closest stellar neighbor. And here is the uncomfortable reality: with the fastest spacecraft humanity has ever built, it would take tens of thousands of years to get there. Not decades, not centuries. Civilizations would rise and fall before the ship arrived. Languages would evolve. Borders would shift. Everything we know would be unrecognizable. And that's just the nearest star. Tonight, we're going to understand why that journey may be forever beyond our reach. Not because we lack courage, not because we lack intelligence, but because the universe itself imposes limits that may never yield. Before we go further, if you enjoy calm, deeply narrated science journeys like this one, take a moment to subscribe, like the video, and leave a comment telling me which part of the country you're watching from. Are you listening from New York, California, Texas, somewhere in the Midwest? I love seeing how far these ideas travel across the map. Now let's begin with distance, real distance, and why it defeats us before we even ignite a rocket. When we say Proxima Centauri is 4.25 light-years away, the human brain struggles because it evolved to navigate forests and plains, not interstellar gulf. So let's scale the solar system down to something we can visualize. Imagine shrinking the sun until it is the size of a tiny period at the end of a sentence, about 0.5 millimeter wide. At that scale, Earth would orbit roughly 3 centimeters away, about the width of 2 fingers. Jupiter would be several meters out. Neptune, the outermost major planet, would circle roughly 100 meters from our tiny sun. Voyager 1, humanity's most distant spacecraft, launched in 1977 and traveling for nearly half a century, would be just a bit farther, perhaps a few hundred meters from our shrunken star. That is the entire domain humanity has ever physically reached. Now, keep in that exact same scale, where would Proxima Centauri be? Not across the room, not down the street. It would be about 8 miles away. 8 miles from that tiny period-sized sun to the next closest star. That's the equivalent of placing our solar system in downtown Los Angeles and putting the next star somewhere near the Pacific coastline. And everything in between, empty. Vast, almost perfectly empty space. This is the first barrier. Interstellar space is not crowded. It is a desert beyond comprehension. The average distance between stars in our region of the Milky Way is measured in light-years. Inside our solar system, distances are measured in light-minutes or light-hours. The jump from interplanetary to interstellar space is not incremental. It is exponential. To understand why this matters, we need to examine speed. Humans are deeply proud of speed. We broke the sound barrier in 1947. We put astronauts on the moon in 1969. The Parker Solar Probe, the fastest human-made object ever built, will exceed 430,000 miles per hour relative to the sun. That sounds astonishing. And it is. At that speed, you could travel from New York to Los Angeles in under 30 seconds. But compared to light, 430,000 miles per hour is barely moving. Light travels at about 670 million miles per hour. The Parker Solar Probe reaches roughly 0.64% the speed of light. That's not 6%, it's 0.06%. At that speed, reaching Proxima Centauri would take around 7,000 years. And that assumes you could aim it directly outward and maintain maximum velocity the entire time. Which we cannot. More realistically, with conventional chemical rockets like those that launched Apollo or the Space Shuttle, we're talking about 30,000 to 70,000 years. That is longer than recorded human civilization. When the pyramids of Egypt were built, it was about 400 or 500 years ago. A 30,000-year journey would stretch back to a time when humans were painting on cave walls in the last ice age, so even our fastest achievements reduce us to stillness against the scale of the galaxy. This brings us to propulsion. Why not just build a bigger rocket? Why not strap on more fuel? The problem lies in a principle called the rocket equation, formulated by Konstantin Tsiolkovsky in 1903. The equation describes how much velocity you can gain from a rocket based on the exhaust velocity of its propellant and the ratio of its starting mass to its final mass. Here's the cruel twist. Every bit of fuel you add increases your mass, and increasing mass requires even more fuel to accelerate. It's a compounding problem. To significantly increase speed, you need exponentially more propellant. If you tried to accelerate a spacecraft to even 10% the speed of light using chemical rockets, the amount of fuel required would exceed the mass of planets, literally planets. Chemical propulsion is fundamentally inadequate for interstellar travel. So what about nuclear propulsion? Nuclear fission releases millions of times more energy per reaction than chemical combustion. Nuclear fusion releases even more. Concepts like Project Orion in the 1950s proposed detonating nuclear bombs behind a spacecraft to push it forward in a series of controlled explosions. On paper, it could reach perhaps 3 to 5% the speed of light. Even then, the journey would take over a century. And that's assuming perfect engineering, no political barriers, and materials capable of surviving repeated nuclear detonations. Fusion propulsion, if mastered, might reach 10% the speed of light. That would cut the trip to Proxima Centauri to about 40 years, within a human lifetime. But here we collide with the next barrier: energy. The kinetic energy required to accelerate even a modest 1,000-ton spacecraft to 10% the speed of light is staggering. The formula for kinetic energy is 1/2 mass times velocity squared. Velocity squared is the killer. When velocity increases by a factor of 10, energy requirements increase by a factor of 100. To accelerate that spacecraft to 0.1 C would require energy comparable to the total annual electricity production of the entire United States multiplied many times over. And that's just to accelerate. You also need to slow down when you arrive. Otherwise, you simply streak past Proxima Centauri at 30,000 kilometers per second, unable to stop. So double the energy, at minimum. Energy is not just a technical challenge, it's an economic and planetary scale challenge. And then there's relativity. As you approach significant fractions of the speed of light, Einstein's theory of special relativity begins to dominate. Time dilation means that time on board the spacecraft would pass more slowly relative to Earth. At 90% the speed of light, a journey that takes 4.7 years from Earth's perspective might feel like only about 2 years to the travelers. That sounds promising, but achieving 90% light speed requires energies that approach the output of entire stars. The relativistic kinetic energy increases dramatically as you get closer to light speed, tending toward infinity as you approach C. This is not an engineering inconvenience. It is a law of physics. Objects with mass cannot reach the speed of light because doing so would require infinite energy. Physics does not negotiate. Even if we solve propulsion and energy, another obstacle awaits interstellar medium. Space between stars is not perfectly empty. It contains sparse hydrogen atoms, dust grains, and cosmic rays. At everyday speeds, these particles are harmless. But at 10% or 20% the speed of light, even a microscopic grain of dust becomes a high-energy projectile. A collision with a grain the size of sand at relativistic speeds would release energy comparable to an explosive device. Shielding against such impacts would require thick protective layers, which increases mass, which increases energy demands, which circles us back to the rocket equation. Everything compounds. Everything resists. And yet, perhaps the most profound barrier is not technical but temporal. Human civilization operates on short timescales. Political cycles last years. Economic planning stretches decades at most. Interstellar missions would require commitments lasting centuries. Who maintains a spacecraft for 500 years? Who ensures its descendants remember the mission? A multi-generational ship introduces sociological uncertainty. Cultures evolve. Beliefs shift. The original purpose may be forgotten. Even if we send robotic probes instead of humans, we must accept that the data they return would arrive decades after launch. The people who approved the mission might not live to see its results. So when we ask why we will never reach our next star, the answer begins to emerge. The barrier is distance amplified by physics, enforced by energy, complicated by time, and guarded by the structure of space-time itself. It is not that Proxima Centauri is impossibly far in absolute terms. It is that the universe's speed limits energy costs and scaling laws that turn just 4.25 light-years into a nearly insurmountable gulf. In the chapter's head, we will explore every proposed solution: generation ships, suspended animation, antimatter drives, laser sails, wormholes, warp drives, and examine them not as science fiction, but as physics problems. We will ask not what we wish were possible, but what the equations allow, because the truth is both sobering and awe-inspiring. The cosmos is open to our eyes, but perhaps not to our footsteps, and understanding why may be the most important journey of all. If distance is the first wall standing between us and the next star, energy is the second, taller, thicker, and far less forgiving. In Chapter 1, we confronted the raw scale of 4.25 light-years and the brutal mathematics of the rocket equation. Now we go deeper, because even if we accept that the stars are unimaginably far apart, there is still a tempting thought that lingers in the back of the mind. Surely, with enough technological progress, with enough innovation, we can eventually build something powerful enough to cross that gulf. After all, human history is a story of barriers falling. We once believed the sound barrier was impossible to break. We once believed powered flight was fantasy. We once believed reaching the moon was beyond our lifetime. And yet we did all of it. So why should the next star be any different? The answer lies in the difference between engineering problems and physical limits. The sound barrier was an engineering problem. The moon was an engineering problem. Interstellar travel is not just an engineering problem, it is a physics problem. And physics, unlike engineering, does not yield to optimism. To understand why energy becomes such a brutal constraint, we need to think not in terms of rockets and fuel tanks, but in terms of fundamental quantities. Energy is the currency of motion. The faster you want to go, the more energy you must pay. But the cost does not rise in a straight line. It rises with the square velocity. Double your speed and you need 4 times the energy. Increase your speed tenfold, and you need 100 times the energy. This simple mathematical relationship quietly destroys most interstellar dreams before they leave the drawing board. Let's consider something modest. Not a giant colony ship, not a city among the stars, just a relatively small interstellar probe weighing 1,000 tons. That is about the mass of a modern naval destroyer, or a small skyscraper laid on its side. Now imagine we want to accelerate it to 10% the speed of light. 10% does not sound outrageous, it sounds cautious, conservative. After all, light speed is the ultimate limit, so surely 10% is manageable. But 10% of light speed is about 30,000 kilometers per second. At that velocity, our 1,000-ton spacecraft would carry kinetic energy on the order of 4.5 × 1020 joules. That number is so large it becomes abstract, so let's translate it. The total annual energy consumption of the entire United States is roughly 1020 joules. So accelerating that single spacecraft to 10% of light speed would require several years' worth of total U.S. energy production. And that's assuming perfect efficiency with no losses, which is impossible. And remember, you must also slow down when you arrive, so double it, and that is just for 10%. If you aim for 20% of light speed, the energy requirement quadruples again. This is the energy wall. It is not just about building a bigger rocket. It is about harnessing and controlling energies comparable to planetary civilizations. Chemical rockets are immediately disqualified. They release energy through rearranging molecular bonds, powerful for launching satellites, laughably insufficient for interstellar acceleration. Nuclear fission is millions of times more energy-dense, but still limited. Nuclear fusion, the process that powers the sun, releases even more energy. Fusion propulsion is often described as our best plausible pathway to interstellar travel. But even fusion, extraordinary as it is, struggles under the tyranny of the energy equation. And then there is antimatter, the most energy-dense fuel we know. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's equation, E = mc². 1 gram of antimatter reacting with 1 gram of matter would release about 1.8 × 1014 joules, roughly equivalent to tens of thousands of tons of TNT. Antimatter propulsion sounds like science fiction, but it is grounded in real physics. The problem is production and storage. Humanity has created antimatter in particle accelerators, but only in minuscule quantities, nanograms at enormous expense. To fuel an interstellar spacecraft, we would need kilograms. Producing that much antimatter would require energy outputs that dwarf global production. Storing it safely would require perfect electromagnetic containment. A single containment failure would release energy comparable to a nuclear weapon. Antimatter is theoretically powerful enough. Practically, it borders on impossible with foreseeable technology. Even if we imagine a future civilization capable of harnessing these energies, we encounter another layer of difficulty: heat. Energy conversion is never perfectly efficient. Waste heat must go somewhere. In space, the only way to shed heat is through radiation. That means enormous radiators, vast panels glowing red-hot, bleeding thermal energy into the void. The faster and more powerful your propulsion system, the more waste heat you generate. Managing that heat without melting your own spacecraft becomes a design challenge of extraordinary scale. But suppose, just for a moment, that we solve propulsion and energy. Suppose we build a fusion-powered spacecraft capable of reaching 10% or even 20% the speed of light. Suppose we shield it against interstellar dust and cosmic radiation. We still face a deeper problem, one woven into spacetime itself. Special relativity does not merely impose a speed limit. It changes how time and energy behave at high velocities. As you approach the speed of light, your relativistic mass increases from the perspective of an outside observer. The energy required to continue accelerating grows more and more steeply. The closer you get to light speed, the more energy you need for each additional increment of speed. The curve becomes asymptotic. You can approach light speed, but you can never reach it. Infinite energy would be required to cross that boundary. This is not a technological shortcoming. It is a structural property of reality. The universe has a built-in maximum speed. No clever engineering can bypass it. No breakthrough material can override it. It is embedded in the geometry of spacetime. When we say we will never reach our next star, what we really mean is that the universe does not permit shortcuts beyond certain thresholds, and yet human imagination resists surrender. If we cannot reach light speed, perhaps we can cheat. Perhaps we can bend space instead of moving through it. This is where concepts like warp drives and wormholes enter the conversation. The Alcubierre warp drive, proposed in 1994, suggests compressing space in front of a spacecraft and expanding it behind, effectively allowing the ship to ride a wave of distorted spacetime faster than light without locally breaking the speed limit. Wormholes, hypothetical tunnels through spacetime, could connect distant regions like shortcuts. These ideas are mathematically consistent within general relativity, but they require exotic matter with negative energy density. No known substance in the universe behaves that way on macroscopic scales. Even if tiny quantum effects hint at negative energy in limited context, scaling it up to a starship-sized warp bubble would require energies comparable to entire stars or galaxies. In some early calculations, the required energy exceeded the mass energy of the observable universe. Later refinements reduced the requirement, but it remains far beyond anything humanity could realistically harness. Warp drives and wormholes are not ruled out absolutely, but they remain speculative to the extreme. They depend on forms of matter and energy we have never observed in usable quantities. Meanwhile, time marches on. Even if we accept a journey lasting centuries, we face human limitations. Biological humans are fragile. We require air, water, food, protection from radiation, psychological stability. A multi-generational ship introduces immense complexity. Thousands of people would need to live, reproduce, govern themselves, and maintain advanced technological systems for centuries in a closed environment. Ecological balance would have to be perfect. A single systemic failure could doom the mission. Social instability could derail it. Cultural drift might cause future generations to question why they are traveling at all. Suspended animation or cryogenic preservation is often proposed as a solution. Put astronauts into deep sleep for decades. But we currently have no reliable method for freezing and reviving humans without severe cellular damage. Even if we solved that, long-duration exposure to cosmic radiation poses another threat. Outside Earth's magnetic field, high-energy particles from the Sun and distant supernovae constantly bombard spacecraft. Over decades, that radiation accumulates, increasing cancer risk and damaging electronics. Perhaps the answer is not to send humans at all. Robotic probes are lighter, more durable, and do not require life support. Projects like Breakthrough Starshot propose sending gram-scale probes attached to light sails propelled by powerful Earth-based lasers to perhaps 20% the speed of light. At that velocity, they could reach Proxima Centauri in about 20 years. This is one of the most realistic interstellar concepts currently under discussion. But even here, immense challenges remain. The laser array required would need to generate gigawatts of precisely focused energy. The sail would have to withstand enormous acceleration forces. Communicating back across 425 light-years with a transmitter the size of a microchip would be extraordinarily difficult. And upon arrival, the probe would not slow down. It would fly through the Proxima system in minutes, capturing fleeting data before disappearing into the darkness. So even our most optimistic near-term concepts do not deliver exploration in the traditional sense. They deliver flybys, glimpses, snapshots. At every turn, physics narrows our options. Energy requirements escalate. Propulsion systems grow more complex. Shielding becomes heavier. Timelines stretch. Communication delays lengthen. The dream of stepping onto the surface of a planet orbiting another star begins to feel less like an engineering roadmap and more like a meditation on limits. And yet, understanding these limits is not a story of defeat. It is a story of clarity. The universe is not obligated to be accessible. It is vast beyond evolutionary convenience. The same laws of physics that allow stars to shine and atoms to form also impose boundaries on motion and energy. Those laws have been tested with exquisite precision. They have never once bent to human desire. When we look at Proxima Centauri in the night sky, invisible to the naked eye, hidden among the southern stars, we are not just looking across distance. We are looking across a boundary defined by energy, relativity, time, and fragility. The next star is not merely far away. It is separated from us by the fundamental architecture of reality.